Hey guys, this is Mr. Sal. We're going to look at and inequalities just after we've gone over or inequalities. Alright, you guys, so this section is about the and statements. We've already covered the or statements, but if we consider the two and the difference between the two, or statements is when an element is part of one or the other. So if we looked at the set A or B, then we get all of these values, even though we don't list them more than once, right? In the set A or B. But now we're looking at the set A and B, so we need values or elements that are part of set A and set B. If they don't meet that condition, then they're not part of the set A and B. So where does this happen? I can see that it happens with the 7 right here, and that's shown in the set, and also the 11 here and here, which is part of set A and B. So that is why we have the 11 in the set A and B. Notice there's no other values because if we look at the elements of set A and B, there are no other elements that are part of both sets. So they don't appear in this list, A and B. Now we need to be careful with this thinking because when we start looking at the actual inequalities, then we need to remember that only elements that are part of one and the other would be true. Specifically, right there it says the intersection, right? So if I were looking at a graph and I had two lines on that graph, let's say this one going that way and perhaps this one going that way, these two lines only intersect between these two values. And we'll look at examples of those here in just a little bit. But also what that means is that this part of the line it's not really there as part of the solution set, and same with that red line right there. It only goes as far as that green line. So we would only be looking specifically in between the two right here. And we'll need to show the intervals for those also. Alright, so we have these two sets, A and B again, and we've already done the or statement for this one. So let's focus specifically on the and statement for this, okay? So the first thing we know that we need is going to be some fancy brackets, something like this. And we'll put a list of all the numbers that are part of A and B. Well, I can find this 32 here and here as part of both sets. So 32 would be part of the set A and B. Next up, I can see the 45s here. They're all kind of stacked together there. So 45 would be part of A and B. And the other element, 47, would also be part of the set A and B. None of the other values in either set appear in both, so they would not be elements of A and B. Alright, let's look at these two right here, and hopefully it will help us to understand what exactly is going on. So this is how it's going to look with compound inequalities, okay? Now remember, we're looking at these values where x is less than or equal to 4, and x needs to be greater than -5, okay? So just think about some values that would work in this solution set, okay? For example, if I said x equals 0, now remember, it's got to be true for both in order for it to be a solution for this compound inequality. In other words, it needs to make both statements true. So the one has to be true and the other has to be true, right? Well, in this one we can see 0 is less than or equal to 4, so that's true. But also 0 is greater than -5, so that would be true. So 0 would be a solution. Let's expand that a little bit. And what if I said that x equaled -10? Well, then it would satisfy the one there underlined in red, x is less than or equal to 4, but it makes the one x is greater than -5 false. So while one is true, the other is false, but we need both of them to be true. So x equals -10 is not a solution for this set. So let's get down to brass tacks here. Let's start with the graphing, and this should kind of help us to visualize what values would make both statements true, okay? So to the left, I would have -5, and then 0 about right there, and 4 on the other end. So I'm going to start with 4, and we'll do it in red. Now that is an equal to, so x is less than or equal to 4, so it's a closed circle. It is not eating x, so this line would go to the left. On the other hand, at -5, that would be an open circle because it's not equal, and this one goes to the right because it's eating the x. Now remember, we need to consider what values would make both of these inequalities true, okay? So, when I consider this, I can see that to the left of -5, it's just the red line, right? So that means there's no green values that would be true for that green inequality, which means that it really just, it kind of stops at 5, right? So we could ignore that part of the red line. Now starting at -5, the red line is still, that -5 makes the red equation or inequality true, but it's false for the green one. So as far left as we go, or as far as left as we can go, would be -5. That's where it's going to start, but it's not included because even though it's true for the red inequality, it's false for the green one. Well, we're going to follow these to the right, and we can see that green and red intersect all of these values between until we get to 4. Once I get to 4, it stops intersecting, or where I've shown on the graph that I have 2 of the lines. But 4 is included in the red inequality and the green one. So it is part of the solution set, meaning 4 would make both of the inequalities true. Now again, as soon as we go anywhere farther to the right of that, the green line right there, then it's no longer an intersection. So we want to be careful with the graphs and show, and we can kind of show those lines, but we need to indicate some way, even if we, like I said, if we had extended the red line or the green one, we need to show that the intersection is between the two. So kind of emphasize that when you guys are doing that on the test. Now remember, this one did not include any solving of the inequalities. They gave us the solutions for those right at the beginning. Don't expect many of the problems to look like this one, okay? This one is just for practicing strictly the graphing and also the interval. But in the future, we're going to have to be simplifying or solving these inequalities for the x values. Alright, so let's get started with these. And I'm going to go ahead and solve these using the principles of equality. I'm just going to do these, and I'm going to show you the work. I'm not going to explain the work. If you need that, then go back to 2.1 and watch how we use those. Okay. Now remember, I need to be careful because if I ever divide or multiply both sides by a negative, then I will flip the inequality. We need to remember that one rule. Other than that, we can pretty much treat these exactly like we would regular equations. So on the left there, after distributing and then using principles of equality, I got x is less than or equal to 12/5. Let's go and start on that one on the right. Alright, so there's our inequalities solved. And again, if you need to just take a deeper look at those, you can pause the video and look at the work for those. I'm going to put my and statement between the two, just so I have acknowledged that it is an and statement. And then we'll go ahead and graph these two lines. So to the far left, I would have -1/2, and then next to that, of course, would be 0, and then 12/5 would be maybe somewhere over in this direction, okay? So at 12/5, we'll start with that one in red. That's a closed circle because it's also equal to, this one's not eating the x, so it goes to the left. At -1/2, I've got an open circle. This one is eating the x, so it goes to the right. But once again, we're just looking for the intersection on these. So I can see that they start intersecting at -1/2. Now that's an open circle there, so it's not included, that -1/2. and then it goes all the way to the 12/5, and that's where it stops intersecting. But it's included for both the red, because that's a closed circle on the red line, and the purple line goes through it as well. So that would be the interval, and overall, of course, this would be our answer. We've got the inequality, the graph, and the interval. Alright, let's go through these ones. Solve graph and give interval notation for the compound inequality. I'm going to do the same thing I did on the last one, where I'm going to do all the work, but I'm not going to explain it, just to save some time on this one, because we need to get down to brass tacks with the graphing and the interval notation. So this one on the left, again, notice I've divided both sides by the -2, the coefficient of x, to get the 1x here. But since I divided both sides by negative, it flipped the inequality here. So on this one here on the right, I've got x is less than or equal to 2 by taking the 6 and dividing 3. Now again, this is an and statement. I'm going to show it even though in the end we actually won't need it, and I'll show you guys why. But before we get to that, let's look at the graph. So on the graph, I've got something as far left as the -6 and something as far right as the 2. So maybe 0 would be right about there. At -6, this one is an open circle, but it is not eating the x, so it goes to the left. At 2, this one would be a closed circle, right here. But it is not eating the x, so it also goes to the left. Now again, we kind of see this interval, that we could say it's starting there at -6 going to the left, but where do they intersect and how far do they intersect to the left? These are going to intersect to the left as far as -infinity. But once we get to that -6, they're no longer intersecting, and the red line has an open circle, so this one is not included. Which means anything to the left of -6 would not only make this inequality true, but it would also make this one true. If we look at the values between these two, such as 0, 0 would make the red one false, while it would make the blue one true. But again, we need one and the other to be true. So we have to be extraordinarily careful on these, because it's going to change the inequality also. The final inequality is not going to be included with these two. I'm sorry, it's not both of them together, even though it is included. And we can see that x would be true for both as long as that it is less than -6. So overall for this one, the three answers, the graph, the inequality, and the interval, would be all three of these. Alright, once again, I'm not going to explain the work on these, but I'm going to show the work so that you can kind of compare what you did with what I did. So on the left there, I get x is greater than or equal to 5. And so I've got x is greater than or equal to 5 and x is less than -4. Let's go and look at the graph on this one. So I've got a value as far to the left as -4 and as far to the right as 5 and 0, somewhere in between there. So at 5, that's the red one. It's going to be a closed circle because it has the equal part of it and it's eating the x, so it goes to the right. The blue one is going to be an open circle at -4, but it's not eating the x, so it goes to the left. Now this looks a lot like the inequalities, or the graphs from the inequalities, of an OR statement. And in that case, we could show an interval which satisfies an OR statement. However, an AND statement on this one indicates that all of the values that would make the blue inequality true would not make the inequality true from the red one. So there are none. There's no intersection on the graph, and that indicates that there's just simply no solutions. Alright, this problem is a true compound inequality, but it is an AND statement. What I mean by that, and I'm just kind of creating an example here. is if I kind of simplify this, right? If I said 0 is less than or equal to x is less than 10, let's say, okay? Well, could you think of some values of x that would make that true? Sure, you could. Anything between 0 and 10, right? So if x were 2, that would be true, or 5.5 or 7.75. Any of those values would make this true. Now, just like with the equalities, though, or principles of equality, this one is comparing three separate parts of an inequality, which means that the principles of equality are going to apply to all three of these. So, for example, if I were to add 3 to the x, I'd have to add 3 to the 0 and to the 10. That would give me a new inequality of 3 is less than or equal to x plus 3, which is less than 13. Now, of course, as we proceed with these in the future, we're not really dealing with adding to the value unless it's to zero something out or make it a 1, okay? So, in this case, you would start with the purple one, and then what would you do to isolate the x? You'd subtract 3 from all three parts, and then you would get the same inequality that we started with. 0 is less than or equal to x, which is less than 10. So that means that all of the values that make the purple one true would make the original one true as well. And again, that's because all we've done is performed a principle of equality. They are communicating the same thing, and they're equivalent, but they're shown very differently. So let's apply this principle to this one, except there is distribution on this one. Now, if we distributed one, we don't need to distribute to all because it's kind of like an equation, right? It's only applying to that factor from the multiplication. So this changes into 2x minus 6. So negative 3 is less than 2x minus 6 is less than or equal to 4. Next, I will add 6 to all three parts. Again, that's to maintain the equality nature of this inequality. So negative 3 plus 6 is 3, which is less than, now it's just 2x, because the 6 is zeroed out there, and that's less than or equal to 10. Finally, we'll divide all of these by 2. Why? To get 1x. So I've got 1x, and in comparison to 3 halves is less than 1x, which is less than or equal to 5. So what does this look like on a number line? Well, the 3 halves and the 5 kind of represent the equality part of this, okay? So 3 halves would be about right here, and 5 somewhere over in this direction. But this does, it actually splits this up into two separate inequalities. So I could compare this as 3 halves is less than x, that would be 1, which means that 3 halves, I'd have an open circle. It's eating the x, so it goes to the right. And on the other hand, I've got x is less than or equal to 5. So at 5, that would be a closed circle going to the left. But we know, just based on the original inequality, that it's all the values sandwiched between these, meaning that these would stop at 3 halves and 5. So we kind of can put a barrier between these two, and all the values in between would make the original inequalities true. The last thing we need on this is the interval. So we know it starts at 3 halves, and that's an open circle in one of the blue lines. So it's not included. And going to the right, it stops at 5, which is included for both. So it's included as the and statement for the original inequality. So anything between 3 halves and 5 would make this original inequality true. It's something that would be greater than negative 3, but also another thing that would be, or the same thing, is still less than or equal to 4. Alright, so let's go ahead and try this one as well. Again, principle of equality, I'm going to subtract 1 from all three parts of this inequality. So I got negative 4 is less than or equal to half of an x, which is less than or equal to 4. Finally, we'll need to multiply this middle part of the inequality by 2 so that I get 1x, which is what we want. But again, if I do it to 1, I've got to do it to all 3. So on this one, 2 times negative 4 is negative 8, which is less than or equal to x, which is less than or equal to 8. So this is the inequality. Of course, next up we would want the graph. And again, I'm going to show it as 2 separate inequalities, because negative 8 is less than or equal to x, but also x is less than or equal to positive 8. So here's my negative 8, there's my 8, 0 would be right in the middle of those two. And the one inequality shows at negative 8 would have a closed circle, it's eating the x, so it goes to the right. The other 8, still a closed circle, it's not eating the x, so it goes to the left. So all the values between these, including the negative 8 and the positive 8, would make the original inequality true. Well, that brings us to the interval. So starting at negative 8, that's where the intersection begins. It's included because it's a closed circle for one of them, and the line just passes through it in the other one. And it goes all the way to 8, which is still included because it's a closed circle and the other line passes through it as well. So we do have the inequality, which really is this one right here, and the graph, and the interval. Alright, on this one, same deal. Principles of equality, but for all 3 parts. So the first thing I'm going to do is add 5 to all 3 parts. So I've got 3 is less than or equal to 3x. 5's zeroed out. That's less than 12. Then we'll divide all of these by 3. And I got 1 is less than or equal to x, which is less than 4. So the graph now, with 1 and 4, x is between these, and at 1 would have a closed circle, at 4 it's open, so it should be everything between these. And that takes us to the interval, which starts at 1, which is included because it's a closed circle. It goes all the way to 4, which is not included because it's an open circle. Now I skipped writing the 2 separate inequalities on this one. If you wanted to, you could. If you did, you should have gotten these 2. And that would have shown that we would have had the same graph and the same interval. Alright guys, that pretty much does it for this lesson. I know it was a lot of stuff, and it kind of had 2 parts with that different looking compound inequality with the 3 parts like this example. So thanks for watching. If it helped you out, or if you liked it, please do like the video, subscribe to the channel, and make a comment below.